Okay, so so the final outcome that we want out of this class is this report summarizing your model. Um, some COVID-19 information. Uh, a lot of this is just our general policy that I put into the syllabus. But like I said, classes will probably be recorded. I'll let you know if that's the case. We have to wear masks in the classroom. So we didn't do it today, but as class goes on, you guys should go get cleaning supplies and masks from and we'll clean our desks before and after class. All right. And there's a refill station for cleaning right across the way. We can grab disinfecting wipes from there too, actually. And we'll just wipe our desks down after class. Other than that, we'll try not to hang out we don't have a really crowded class, so I'm not super worried about a lot of this stuff for us. If you're feeling ill, don't come to class, and feel free to talk with me about any kind of workarounds that we can come up with. Okay, so then there's a sort of rough schedule of what we're going to try and cover in class on the back page. I'm hoping that we can kind of stay with this schedule. We'll see how it goes as time goes on. All right, and we'll modify as we need to. So if you look at this schedule, there's sort of topics that we're going to be discussing for each week. And then there's, in this other column, there's sort of reading or other activities that I want you to do on the side, and then homework deadlines. So this will be our rough template for the course. Now, let's talk a bit about course format and how I'm visualizing course is going to work this year. I think that probably chances are good that at some point we're going to go full online. I'm at least planning that way. We have at least one, if not two students who are going to be participating mostly online. So I'm going to try and teach this I've never taught this way, but I'm going to try and flip the classroom. And the basic idea with a flipped classroom is that I will record a canned lecture on a topic, and you guys watch that on your own time. And that our in-class periods are our time to work on activities, all right? And to try and do real active learning and applications. So for this class, what I was thinking is all lecture, and between the lecture and the online recorded lecture and the reading, you'll get your background, and that in class we'll spend our time working essentially on our homework assignments and getting simulations running. All right. So that's my plan, but I'm going to say this. I am I've never done it this way, and I want to be flexible, and I want to make sure you guys are getting what you want out of the class. I recorded my first lecture the other day, and it kind of sucks. I really don't like to just lecture. I like dialogue. So if it's really boring for you guys to listen to these lectures and you would rather do the assignments on your own, then just let me know, and we can flip the classroom back to the normal way. But for now, I'm going to try this flipped classroom. The nice thing about it is it gives people a real high level of flexibility in terms of when and how they attend class. And And it allows us, I think, to spend more time working together to try and solve your problem. So one of the things I found in this course over the years in previous times is that we always ended up at the end of the year without the students getting as much done on their model as they needed to. And so I think by flipping it, I can help you guys move forward in the modeling and solve these initial problems earlier and faster. So that's my idea. So I will try and post the lectures at least a day or two in advance, so give you guys time to watch them. And then that next class period, we'll just be working on activities in class, all right? And I'll record that work so that other people who are working on those activities can use that if they're not able to make class at that time period. And as I said, we don't have a whole lot of people in class. We're going to have 4, maybe 5 people in class. It's a graduate level course, so you know, I want you guys to know that you have more leeway in designing the course than you do in an undergrad. All right, especially the grad students. You guys want to get out of this what you need. And so if something's not working for you, please let me know. We can be really adaptable. And this is, you know, an especially weird year to be teaching. So, so just let me know what I can do to improve the experience for you guys. Okay. So like I said, we're going to focus around modeling and simulation of groundwater problems. So the first thing that I want to do is make sure that we have got just the basics that we need installed on your computer to get started. So did anybody, let's see, I asked you guys to get some kind of a bash terminal, depending on your machine, and Python installed. So is there anybody that doesn't have that right now? Yeah, if you just open terminal, you've got a bash. And you do? Are you running Windows or Linux? Windows 10. All right, but it can do the bash. It's got a Linux terminal. Okay, great, cool. Perfect. And you're good, Claire?
I've got something has gone. I have a dash ZSH going on. Does that sound familiar when I open terminal? And instead of having a $sign after the command prompt, it has a % sign, which I've never seen before. So I'm not entirely sure.
I think it sounds okay, but we'll see what happens.
We'll see what happens. I mean, Anaconda opens, so.
Okay, so another reason why I've decided to try and teach more on the ModFlow side is we can do a lot of we can install ModFlow and do all the sort of pre-processing and post-processing for ModFlow with a Python package called FlowPy. And that sort of takes any kind of operating system shenanigans out of the equation. So that's what we'll start doing starting next week, is really getting FlowPy installed and ModFlow. But previously I taught the class using pflowtran, and it's like really hardcore Linux based. You guys with Windows 10, you can build it, but it's a nightmare. And so you're usually just logging into my Linux machine. And we may end up there by the end of the year if this mod flow thing doesn't work, but I'm hoping by using FlowPy, we can get away from any kind of operating system issues, and we're just using Python exclusively, and that works on any operating system. Okay, so it sounds like we're doing at least pretty good so far on the computer stuff. One of the things I anticipate as we go forward is we're going to have issues with people not being able to get stuff installed. And so that's another thing we'll be doing during class periods, is trying to troubleshoot and get things installed for people. That being said, I'd rather not use class for that. So if you're having issues, email me and we'll try and work them out offline, but that's what class will be for as well. All right. What else did I want to hit in terms of logistics? I think that's about it. All right. So I will hand out our first homework assignment here. So did anybody have time to watch the lecture that I posted last night? So Jarrett, Yoon. So the idea was just to, if you hadn't taken hydrogeology, yesterday was probably a little intense, but if you have taken especially my hydrogeology class, so it's a quick review of what some of the stuff we covered, just to get us thinking about porous media and groundwater flow again. All right, so the first thing I want to do is start off by tackling homework assignment number 1, or question number 1. And that is to derive the groundwater flow equation for confined aquifer flow. All right, so I'm gonna give a hint to start, and that is conservation of mass. Is our base, and also that we always start these derivations with a box. All right, and here we've got a box of porous media. And usually we give that box some dimensions of delta X, delta Y, and delta Z. So here's our coordinate system of X, Y, and Z. All right. So conservation of mass, what's the first step to deriving this thing? What do you guys think? What's the first thing we should do? Ah,
Fluxes.
okay. So something about flux in and flux out. I like it. Okay. So let me see if I can find a blue one that works. All right, so some kind of flux in, flux out, change in mass is equal to, well, is it really though? Is the change in mass equal to the flux in minus the flux out? Okay, I like that. I like that better. I like that better. We're staying in the right unit. The change in mass in our box is equal to the mass coming in minus the mass going out. I like that a lot. That's a good first stop. Okay, so how would we calculate how much mass is in our box? Okay, so yeah, good point. I'm gonna say that all of our pore space here is fully saturated with water, and the mass that we're interested in is the water mass. All right, so we need to know the material, and all we care about is the amount of water in our box. So what is the amount of water in the box? Okay, so I'm going to say all the pore space is full of water. So it's fully saturated with water. So you're right. You're on the right. So let's think about something. So I agree with Jarrett that it's going to have something to do with porosity, right? Oh, also, I'll let you guys know, I have to leave at 3 today. I have to go testify to the faculty senate. So today's class is going to be a little short. All right, what do you think, Claire? How can I calculate the amount of mass in my box?
The mass density of grains times the volume of grains plus the density of water times the volume of water.
Okay, so let's say I don't care about the grain, so I just want water.
So porosity times total volume times density.
I like it. Okay, so you guys see what she's doing? She's saying, okay, we got this cube. What's the total volume of my cube here? How do I calculate that?
Delta X, delta Y, delta Z.
Yeah, delta. So total volume is delta X times delta Y times delta Z. All right, but not all of that volume is water. So we got to multiply it by porosity, right? Times N times rho water, right? The density of water. So that one right there gives me the total amount of water mass in my box. Okay. I'm going to add something to our initial mass conservation statement here, and that is that the change in mass with respect to time is how much mass is coming in minus how much mass is going out. Okay, so we've got total mass, and I'm gonna put it over a delta t. So that's this term here now is the total mass. How much is the total mass in my box changing with time? All right, so let's just focus in on one direction, say flux across the x, these two planes in the YZ, just the x direction fluxes. So how would I calculate the mass into our box? Yeah, but let's just do the x direction this time. So how can I calculate how much water is coming into the box? Okay, I like it. We're going to need to know the area. And if it's coming across this side of the cube here, what is that area? Yeah. All right. What else do I need to know? Okay, I got area.
Your
What
rate.
else?
You need a rate.
Okay, what's the rate?
It'd be kilograms per time.
Okay, how do I get, so Yoon says I need flux. I agree. So let's do QX. That's this guy. I like that. And how do I turn that into kilograms, Claire?
I can't, does it say QX equals delta Y delta X?
QX times delta Y times delta X. So the flux, this is the flux in. It's the flux. How do I turn flux into kilograms?
Divide by density.
Multiply by density.
Oh, right.
Okay. So this one here, this is flux in. So this one's M in, or mass in. Now the whole trick here is how do we do the mass out? Okay. So Yoon says, oh yeah, easy. Rho water times QX out, delta Y, delta Z. And I agree that is what the flux out is. I agree. There's a trick we have to do to derive the groundwater flow equation to figure out what that flux out is. This is the whole trick to deriving the continuity equation right here. Does anybody got any ideas? I'll give you a hint. I want to write this in terms of this. See, right now I
Assume
got two
constant.
fluxes. I want to relate those two fluxes.
Assume constant density.
We're going to do that too. But right now, independent of density, I just want to think about how can I write this flux in terms of this flux? Got any ideas? Oh, Yin's on it. Okay. So what? So we could write this guy as the flux in plus the change in the flux dq dx. All right. That is, how much does the flux change? All right. And then we got to multiply that change by the length. So we have some gradient and we say it's changing at some rate, and we need to know the length to figure out what the total change is across the length of the cube. So this step is really critical. This step is writing the flux out in terms of the flux in. It's just the flux in plus the change in the flux across the length of the cube. Claire, you probably can't see that anymore, can you?
Yeah.
That's a little better. Okay, so now I can write this equation, delta x, delta y, delta z, n rho water over delta t. And that's equal to my mass in, rho water q sub x times delta y times delta z. Right, mass in. And then I'm just gonna do some algebra here. So minus rho water times qx times delta y times delta z minus rho water Okay, so I've got mass, the change in mass, delta M is equal to M in minus M out. Now, how could I simplify this equation here? We could do that. We're going to hold off on that, but I agree, we can. But I don't want to do it quite yet. What else can I do? Well, yes, I think we can do that too, but I don't want to do that yet. The reason why I don't want to do that yet is this volume, if I divide it over here, I still have, I don't have a delta X on this one. So I'll have this 1 over X thing. That's really complicated. We're not going to do that yet. What is this term minus this term? It's 0. First thing I can do is just get rid of those two. So these go away, and I get this. Okay. I'm liking what we're doing so far. The next thing I want to do is, well, what's the next move? What do you think? Yeah, get rid of that volume. So we can cross these out. And rho water, delta T. So this right here, this equation, and in fact, I'm gonna, instead of delta T here, I'm gonna make this a derivative. So dN rho water dt. That okay with people? So the change in mass with time is equal to the change in the flux with respect to X. This is in the X direction. All right, so we could repeat that same procedure for each direction, right? It would be the exact same to do it for the Y direction and the Z direction. So how do you think that would change this equation here? Yeah, and if we do it for all three at once, all we do is we just keep adding this. So rho water, dqy, dy, minus rho water, dqz, dz. This equation in engineering is called, it's got a special name. It's called the continuity equation. Continuity equation. And it's just a statement of conservation in mass, and all it says is the change in mass with respect to time is equal to the difference between the fluxes coming in and out. This also gets called the divergence of the flux field. So it says the change in mass with time is equal to the divergence of the flux field. That's the continuity equation. All right. I got 5 more minutes before I got a boogie. What do you think you do to make that a groundwater flow equation now? Well, let me put it this way. In order for it to be very useful for us, we can't, it's really hard for groundwater hydrologists to go out and measure a groundwater flux. Like there's no way we just go into a well and measure groundwater flux. So we don't want, what's that?
Change it into head.
We want to change it into head.
Change it
head. So how are we going to do that?
The fluid potential you're talking about.
How do we relate fluid flux to head? What's the relationship between fluid flux and head? Like if I wanted to calculate the groundwater flux and I had 2 head measurements, what would I use?
The difference in the head. Like that's the force gradient that it's.
Yeah. So what's that? Something like every time we started groundwater, I usually asked, what is the main law we talked about in groundwater? Darcy's. Right? Darcy's law. What is Darcy's law? What's Darcy's law?
Hydraulic conductivity DHDL times area.
Yeah. Or for flux, like in the x direction, it would be negative K dH dx. Right? So this relates flux to a gradient in head. That's what Darcy's law does. So we can plug Darcy's law in here. Well, in for Q of X, right? We just plug this guy right in here. For Q of Y, negative K dH dy goes in there. And negative K dH dz goes in there. All right, there's only one more thing we need to do. And that is to turn the change in porosity and the change in density with time into change with head. Anybody remember?
That's how we bust out Bernoulli's equation, right?
No, you don't need it. Well, basically, we had this term, the specific storage that was rho water G times the compressibility of water plus, or the compressibility of the porous matrix plus porosity times the compressibility of water. All right, and what the specific storage was how much water we would get for a change in head. So this term here is the change in porosity. That's the compressibility of the porous matrix. And the change in water density, that's the compressibility of the water for a unit change in head. So I can use this guy can become SS DH dt. All right, so all you guys got to do is plug in this, and this, and you'll have number 1 done. All right, I got to go talk to Faculty Senate. I will post a copy of the next lecture, or I'll record a copy of the next lecture tomorrow. That's my plan. And then on Tuesday, we'll meet at the same time. Sound good? Okay.
Thanks, Peyton. We'll have to see if we can experiment with seeing the board better. See if we can come up with something for that. But
okay. Maybe what we need to do is put the camera up closer. But yeah.
Yeah, that might work.
I could also, you know, Claire, the other thing to do is that I start taking notes on the computer and projecting it onto the screen. That's probably the best way to handle it.
Yeah, I mean, we can also just try the easy way of sticking it next to, sticking it closer to the board for right now and get more complicated if we need to.
Okay. All right, well, we'll try that next time.